Hello everyone, I am Debojyoti and today I am going to present to you an optimization algorithm which my collaborators and I developed. The algorithm that we call AGGLIO works on functions which are only locally convex and gives provable global convergence guarantee. Let's first look at our problem setup. The model we focus upon is generalized linear model. It is defined by the activation functions phi, which maps the input feature vector x into corresponding label y. The learning objective here is to estimate the unknown model parameter w star. There is a noisy version of it as well. For classical GLM involving sigmoid, Poisson, etc. as activation, the estimation of w star can be done by solving an equivalent convex MLE formulation. However, this method is not extendable for activations like JLU, SoftPlus, etc., which are popular in deep networks. Hence, we minimize task-specific loss function like least square loss for regression and binary cross entropy for classification problem, given by the following equation. W hat here is the estimator of W star. Even though the objective functions like squared loss has some nice properties, it turns out that such objectives with respect to activations like sigmoid, softplus, CLU, etc. are non-convex. This poses a challenge for optimization algorithm. Interestingly, these objective functions exhibit strong convex region close to their optima. Strong convexity, which assumes a curvature, helps gradient-based algorithms with faster convergence rate. But these local convex regions are too small to be exploited. Our algorithm tries to overcome this problem. The first key idea of our algorithm is to expand the locally strongly convex region by creating a graduated version of our original objective function. In the new objective, we substituted the label and the activation function with their graduated versions. The graduation is with respect to the temperature parameter tau, as presented in the following. We see that setting tau is equal to 1 gives the original ungraduated version. The current slide illustrates for several activations like sigmoid, softplus, etc. how small values of temperature tau expand the region of strong convexity around the optima. The diagram on the left shows how sigmoid, which has sharp and steep slope for large tau, becomes flatter and smoother as tau becomes smaller. The image on the right shows that indeed the loss surface, otherwise non-convex, becomes strongly convex for low values of tau. But this comes at a cost of diminished gradient, which slows down the convergence. Here comes the second key idea of our algorithm, which is to elevate tau incrementally with time. Putting these two ideas together gives us AGGLIO. AGGLIO is an iterative algorithm. Given our training data and activation function, it starts with an initial model W0 and initial temperature tau0. At any time step, AGGLIO first constructs the graduated objective function corresponding to the current temperature. It then uses a descent step such that SGD or Adam on this graduated objective to update the model. Next, it raises the temperature, also ensuring the upper bound by 1. Now, we will briefly tell what kinds of activations for a GLA model gives a suitable objective for AGGLIO. The objective function admitting AGGLIO should have ELSC property. That is, by lowering the temperature tau, the strongly convex region around the optimum can be expanded to enclose any point and vice versa. AGGLIO gives linear rate of convergence. The image on the right shows how the model initialized at a distance from W star is attracted inside as the tau increases, thereby collapsing the strongly convex region gradually. We have performed extensive experiments to validate AGGLIO, both in ideal noiseless as well as noisy settings. Our algorithms offer comparable or better accuracies and faster convergence than benchmark non-convex optimization algorithms like NGD, Yogi, Adam, etc. Our provable guarantees are supported by synthetic as well as real dataset. Thanks for listening.